am Shahnaz. We are now going to study free modules. Actually, modules formally generalize the vector spaces in the sense that in modules the scalars are allowed to be in the ring, whereas in a field in a vector space they are always chosen from the field. The use of modules was pioneered by one of the most prominent mathematicians of the first quarter of the century, whose name is Emil Noether. And she led the way in demonstrating the power and elegance of this structure. Now let us begin this lecture with the definition of module. So before we proceed further, a ring R will always mean a commutative ring with unity. So this is the convention. To say over time, a ring R will always mean a commutative ring with unity. Unless and otherwise stated. So let us define what a module is. So let R be a ring. So we start with a ring R. So an R module M, an R module over R is a set M together with so we have these two items. First item is a binary operation this addition on M, under which M is abelian group. And item second is that we have an action of R on M, and action of R on M, that is a map R cross M to M given by which takes the odd pair this Rm to the element Rm in the module. So this is for all R in R and for all element M. So this action which satisfies this action has to satisfy few conditions. The first condition is that the addition in the ring R. So if we have element, let's say R1 and R2 in the ring R, so this is the addition in the ring R. So this addition must be compatible with this multiplication here. So this must be equal to R1M plus R2M. Similarly, so this is for all R1, R2 in R and this M in M. Second item is that, so if we have an element of R, so this multiplication should also be compatible with the addition in the module. So that is, this is RM1 plus RM2. So this is multiplication here. This is also called the scalar multiplication. The elements of R are called scalars. This is for all R in R and M1 and M2 in M. So the third item C is, so let us consider this multiplication. So this is the multiplication in the ring R, and here this is this multiplication, I mean the scalar multiplication. So this multiplication, which I am not writing here, so this is the multiplication inside the ring. So this multiplication and the multiplication which we have mentioned here, this scalar multiplication, these two multiplications should also be compatible. So that means this should be equal to R1 dot R2M. Again, this is true for all R1, R2 in R and M in M. Finally, the unit element in the ring R, if we multiply this, if we take action by this element on M, so this is M for all M in M. So if M is an abelian group under addition with this extra structure here which satisfies these properties, then M is said to be an R module. Now let us give some examples of modules. So any vector space, suppose we have a vector space, let's say V over a field over a field, suppose K. So any vector space over a field K is a K module. So the second example is any ring R is an R module. So in this case, the multiplication inside R is same as the scalar multiplication. Now if we consider any abelian group under addition that has a Z module structure, so any abelian group under addition has a Z module structure where Z is the ring of integers, has a Z module structure. Now if we consider this set R, so these are the set of all polynomials in one variable, i.e. it consists these sums where this sum is a finite sum, say items from 1 to n, 0 to n. These polynomials, these coefficients are in the ring R. And then this polynomial ring in one variable, this is an R module. So if we consider, so if I is an ideal of R, then I is also an R module. So these are few examples of modules, and these module actions can be easily verified. So we have another definition, that is a definition of a submodule. So let R be a ring and let M be an R module. So let R be a ring and M be an R module. So an R submodule of M is a subgroup, say N of M, which is a module itself. So an R submodule of M is a subgroup, say N of M, which is also an R module, I mean which satisfies these module actions. So this has to be an R module. Now let us define quotient modules and module homomorphisms. Quotient modules and module homomorphisms. So we have another definition. So let us consider R to be a ring and M and N be an R modules. So let R be a ring and M and N be R modules. So a map say phi from M to N is an R module homomorphism. If it respects R module structure. If it respects R module structure, that means if this is module M, this is module N, and this is the map phi. If we take elements A and B here, so element A goes to phi of A and element B goes to phi of B. Now M being a subgroup under addition, if we look at this element A plus B, so this element A plus B, this goes to phi of A plus B. So if this phi of AB equals this thing, I mean if A plus B goes to phi of A plus phi of B, then phi respects the addition structure of M. And also if R is in R and M is in M, so if phi of Rm goes to R of phi M, then we say phi respects the scalar multiplication. Now if phi is a map which respects the addition structure and the scalar multiplication structure, then phi is said to be an R module homomorphism. So that is if it respects R module structure. That is if phi of say M1 plus M2 is phi of M1 plus phi of M2 for all M1 and M2 in M. And the second item is that phi of Rm is R times phi of M for all R in R and M in M. In this case we say this R, this phi is an R module homomorphism, and phi is said to be an isomorphism if phi is bijective, i.e. phi is both injective and surjective, and in that case we write M is isomorphic to N. We denote this by this notation, the fact that these modules are isomorphic. To emphasize, denote M and N are isomorphic. So one can give examples of module homomorphism. So if M is equal to N, then the map phi from M to M, which takes an element M to AM, while A is in R, then this is obviously a module homomorphism. So this is an easy exercise to prove this is a module homomorphism. Now we define the kernel of homomorphism. So we define the kernel of the homomorphism phi from M to N to be the set. So kernel of phi. So we define the kernel of kernel. So this is denoted by kernel of phi. So it consists of all those elements of M whose image under M is the identity element of the module N. So this is the kernel of a module homomorphism. So let us define the cyclic modules. So we have another definition. So an R module M so let R be a ring and R module M is called a cyclic module if M is actually Rx. Now by Rx we mean a group generated by the element X. Now this Rx, this consists of all finite sums of this form AI Xi, where I runs from 1 to n and these AI's are in R. So this is actually this set X. Sorry, this is not I, this is just X. So this is a cyclic module. So let us prove a proposition. So an R module is cyclic if and only if M is isomorphic to. Before that, let us define the quotient module. So let M be an R module where R is a ring and N be a submodule of M. Then the set M mod N, so it consists of elements of the form, say M plus N, while this M is in N. Now this M mod N, this has a natural R module structure. Then M mod N, so obviously M mod n is a group, I mean the quotient group. Now it remains to prove that this M mod n also has this scalar multiplication structure. Then M mod n has a natural R modulo structure. Where the map R cross M mod n to M mod n is given as, so it takes the element, it takes this pair R and M plus n to R M plus n. So this is a structure, R model structure on M mod n. So this M mod n is called quotient modulo. Then M mod n is a natural R model structure, where this is called a quotient modulo. Quotient module of M given by n.